So we'll wait for a couple of more minutes, then start. Let's see if anyone is joined. So yeah, welcome everyone. This is NOC W91 NPTEL tutorial session on semiconductor devices and circuits. So the course instructor is Professor Sanjeev Sambandhan from IIT Bengaluru. I am Debashish Nandi from IIT-K. I am a PMRF scholar. As you know that this has been a 12-week course. So we have almost covered 12 weeks yesterday, and now this will be kind of a summary session. Okay, I'll be discussing some of the problems which I feel will be important for your semester exam or the term paper. Okay, so this will be not a 2-hour session but only 1-hour session. Okay, so let's begin. Okay, so what I expect to from you who are joining live, that please cooperate with me to try to attempt the question. I will try to hold this session in a way that I will ask you to give me suggestions how to solve the questions. Okay, it may be wrong. I know that you have your semester exams parallelly in your respective colleges, so you may not be completely brushing up your entire stuff, but it will be better if you can contribute. Okay, so try to answer the questions how to go about it, and if I see that there is any lacuna in your concepts, then I will try to answer. Okay, so any one of you can unmute and assist me how to solve this question. So what is mentioned that a particle moving in a 1D one dimensional box in a stationary state which have a wave function like this. Okay, so they want us to find out the magnitude of the wave function. So firstly I would like to know that what do you mean by this wave function. I know it has been discussed almost 4 months back, but let's see how much we can remember, right? So what is a wave function? Am I audible, by the way?
Yes, sir.
Okay, so can you please try to answer what is the wave function or a wave function? What do you mean by that? Make a comment. Doesn't matter. It may not be correct or it need not to be. It need not be correct, right? Make a comment.
Sir, it will give the information about the parameter of particle.
Okay, so it will. It is a. It will give
Uh,
all the information
Measurable parameter of the particle.
about the measurable parameters of the particle. Okay, fine. Then what next?
So that's it. It
That's
has
it.
some proper. It has some property that
Okay.
like
What does this mean?
uh,
What is this?
probability density of finding electron.
Probability density of finding electron. Do it need to
Particle.
probability density of finding a particle, right? In a space, let's say in a space dx.
Text.
Okay.
Yes.
So now tell me what is normalization integral?
Normalization. It should be one. It means particle must be present in the entire space.
So the limit of the integration should be minus infinity to infinity, right?
Yes, sir.
So this is also known as normalization integral. So we want to find out the coefficient or the constant coefficient of the this your wave function. So how to go about it? I have told it right in session 1 and 2 that whenever we want to find out the value of a or the constant sitting in front of the wave function, so what do you do? So the general procedure, always remember that whenever you need to find out the value of a, we most of the time, let's say for most always for you guys for this course you take it as always you should use the normalization integral. Okay, so normalization integral is the key to solve this kind of questions where you need to find out the value of a. So if you need to find out the value of a, what will you do? You will do minus infinity to infinity psi star x psi x is equal to 1, right? Then what will you do? You break it into the, you see that beyond, that means you have a profile something like this. This is your x equal to a, this is your x equal to minus a. There are infinite potentials lying, and somewhere here is your particle. So here is your psi is equal to 0, here your psi is equal to 0. Fine. So your integral it boils down to minus a to a, and what is that? Psi star psi. What kind of function is this? What will be the psi star of this? Any comment?
Answer itself. It looks real function, so psi star
Yeah, it is a
should
real
be same.
function,
Yes.
right? Psi can be a complex function, or psi is generally a complex function. So in this case, we are given that it is a real function. So the conjugate of that real function will remain conjugate, will remain real, the function itself, right? So what we have to do, it will become your psi of x square dx is equal to 1. A is given as minus 3. So minus 3 to 3. Psi of x would be a square, and this will be 1 plus cos pi x by 3 whole square dx equal to 1. Right? So how will you solve it? A square you can take outside, and you just need to expand this, okay? So 1 plus 2 cos pi x by 3 plus cos square pi x by 3. Then how to solve it?
1 plus cos square will be sine
This will
square,
be
and then
your
sine.
6, and this will be your 2 sine pi x by 3 over pi by 3, and the limit would be 3 to minus 3, right? And in this case, what will you do? You will take a half outside, and inside it will be 2 cos square theta, right? That you can write as 1 plus cos 2 pi x by 3, and you will integrate it 3 to 3 dx. This will be equal to 1. Then your a square, this will remain 6 plus what will be the sine of pi, minus sine of pi will be there, so sine pi is 0, so this entire term will go to 0, and here you will have half, so 6 over 2 plus here you have what, sine of 2 pi x by 3 over 2 pi by 3, and the entire stuff will go to 3 to minus 3. So in this case you will have, again this will be sine 2 pi, then this entire thing will go to 0, so you are remaining with 9, right? So what will be the value of your a? A will be plus minus 1 over 3. Okay, so what is the crux of this problem? I wanted you to remember from lecture 1 and 2 that whenever you are given a wave function and you are asked to find out the coefficient, you need to always use the normalization integral, okay? There are other conditions also. What are the conditions? Can you remember?
It should be differentiable and derivative should be continuous.
Conditions of psi x. So first thing is well behaved, right?
Yes, sir.
What did I mean by well behaved?
Not certain spike like an
No
impulse function, not
singularity, right?
no
That is called
singularity. Yes, sir.
singularity.
Yes.
And psi x should be continuous. Psi star x should be continuous. By the way, does this always hold? This does not hold, right? For the case of delta potential, we have discussed this.
Yes, sir.
Please go back and check that. So, and other main property is the normalization integral. So these four properties of the wave function you must be familiar with and always keep in your mind. So this is generally used to compute a, okay, or the coefficient. And why these are important? To find out what?
Boundary condition.
Boundary conditions, right? So remember that. Okay. So this is a very important problem actually, and from this is the basis of your quantum mechanics, right? From this wave function you write your Schrodinger equation, and from Schrodinger equation you give the solution, or it is the other way around. The Schrodinger equation solution is your wave function, right? And wave function gives you properties of the particle. From that, then there is the whole domain of semiconductor physics which starts. Okay. So what I suggest you that once you have gone through the entire content of the course, you try to go back to the beginning and try to relate in a block diagram fashion that what were the topics of each lecture weeks, or lecture week number 1 to week number 12, and then connect that how these things are related. It should not be that once you are familiar with the MOSFET circuits, you forget about the quantum mechanics. So you should back of your mind, you should always have that connection, or the dots should be connected back of your mind. Okay, how from quantum mechanics the carrier statistics has come about, and from that how the device loss transports, all those things come about, and how those things were used in the in analyzing the devices like PN junction, metal semiconductor, Schottky barriers, ohmic contacts, MOS caps, etc. Okay, so let's move on to the next problem. Okay, so part 2 task: which of the following statement explain the relevance of effective mass being negative for some particles in solid state physics? Okay, so can you name a particle which has negative effective mass? What is effective mass, by the way?
H square by del 2 E by del in case.
I always tell to my students that when you are asked to find out derivative or curvature or slope, what should you ask first? That which point I should get the derivative. Suppose you have a straight line, okay, and if I want you to tell me the slope, you can tell me the slope, right? Because at each point the derivative remains same. It's just a constant line, okay. But what about any non-linear function? If you are asked to find out the slope or derivative or curvature of the non-linear function, so what will you do? If I tell you to find out the curvature of this function, so what will be your answer? Well, let me ask that what is the slope of this function? Yes.
Sir, find maxima, minima, and then
No,
find
no, right.
add.
Differentiation would be there, but if I want to ask you that, tell me that what is the slope. So
Straight
what should
line parallel to x-axis.
of this function?
Yes, sir.
Straight line will be the slope. See, that is the point, right? Slope or curvature, you should ask me that which point you are talking about. Should I take the slope at this point? Should I take the slope at this point or this point? You know that the slope is always varying, right?
Yes, sir.
So you should always ask that which point I am supposed to find out the slope. Okay. Do you get the point?
Yes, sir.
Now, when I asked you that what is effective mass, What did you tell me? You tell me directly that h bar square by del square E by del K square. But then I should ask you, right? What is the point? Always mention whenever you are writing that formula, always mention that it is at a band minima or band maxima. That point you need to be clear about, that which point you are talking about. Your bands are like this, right? You are taking the value at this point, the curvature at this point, okay, not at this point. It will be a whole lot of different story if you are trying to find out the curvature at that point. So keep that in mind, okay. So now tell me, what do you mean by effective mass, by the way? Means if it is asked in your any job interview, what will you tell, that what is effective mass? Last lecture also I have touched upon that effective mass is nothing but you are assuming that in a crystal potential your particle will move like a free particle, okay. So see, please remember these concepts, these are very important. What is a free particle? What is the definition of a free particle? Can anyone tell me? I will really be impressed if anyone can tell me exactly what is the definition of free particle. You can just try.
It will be free from influence of any kind of field,
Wait, hold on. Free from
any external field.
influence of any field. Okay? What does that mean? What will be its potential energy? What will be its potential energy? If no field is acting upon it, what will be its potential energy?
Zero.
How do you say that? Suppose gravitational field is not working or acting upon you, right? Then you will not have any potential energy,
Yes, sir.
right? If you are having a, suppose this pencil I am holding at this point, so what is the potential energy? It will be mgh, right?
Yes,
Mg
sir.
is the gravitational force and g is the height, and if I put it higher up, then potential energy will increase because it is feeling a field from the gravity. But similarly, in a electric field also, if any charged particle or any particle is not under influence of any field, so its potential energy should be zero. Okay. So what is the energy of a free particle then? Total energy is P plus Ke. So for a free particle, it will be only kinetic energy. Do you agree?
Yes, sir.
So what is energy? You can write P square by 2m. Is that okay?
Yes, sir.
P is your momentum, okay? So crystal momentum you can write h square k square by 2m.
Yes, sir.
So remember that I am able to write this only because I am considering it as a free particle. If it is not a free particle, for which the crystal in a crystal this electrons are not free particles, okay, but to model them as free particle, remember that. So E is your, if E is for a free particle, then only kinetic energy will be there. So your E equal to h square k square by 2m. So what is the mass? Can I write it this form? B square E by dk square. If you take dE by dk, what will you have? If you take dE by dk, you will have h square 2k over 2m, right? 2 will get cancelled and your d square E by dk square will become h square by m. So your m is this, right? So this is for a free particle. Now if I am asking you that what is m star or effective mass. So your answer should be that whenever a particle, or let's say you call it an electron itself, whenever an electron is moving in a crystal potential, the we can approximate that movement of the particle that to that of a free particle. So the corresponding effective mass related to the kinetic energy of that modeled free particle is the is your this formula. Okay, so remember that we effective mass is the a concept which we use only to model the movement of the electrons or any particles like a free particle. Okay, so remember this point. So this is your effective, as far as this is your effective mass. Now let us draw the band diagram, sorry, band structure. By the way, you are aware of the difference between band diagram and band structure, right?
Yes, sir.
So what is band structure? Band structure is EK diagram. What is band diagram? That is
EA
how
diagram.
E,
A, how vary from lattice.
that is distance, right? Not A,
Lattice
it is
distance.
distance, not lattice distance. It is distance along the material.
Yes, sir.
Okay. So if let me draw a, so this is your band structure, right? For let's say gallium arsenide. Okay. Now look at this very carefully. Suppose this is your, what is your E? What is your m star? M star is your h bar square by del square E by del k square. Okay. So this is for your, this is your EC or conduction band minima, and this is your EV. Always remember that these are electronic energy. Okay, that means if we go up, the electronic energy increases. Okay, so let me draw this thing. Suppose this is your a function y over y versus x. So how will this look like? Dy over dx, how will this look like? So this will look like something like this. This will be 0, then there will be a maximum, then there will be a maximum, then there will be 0. Do you agree with this? Is if you take derivative of this function, the black line, you will get the pink line. Do you agree with this, or should I need to or do I need to explain this?
Sir, explain.
Okay, so how to draw a derivative quickly? Okay, see, at this point what is the derivative?
It seems, sir, constant, so derivative should be 0.
Derivative should be 0. What is the derivative at this point? It's a
Sir,
minima,
it
right?
look like parabola, so straight line.
No, it is a minima, right? This one. Don't go after that formulas and all. Just look at the diagram. It is a minima. At the minima, your derivative is 0, right?
Yes, sir.
So it should be 0.
Yes, sir.
So it doesn't matter whether it is a parabola or not. Even if you draw a parabola, at this point your derivative will be 0.
Yes, sir.
Okay. So so these points you are marking in these plots. Okay. Similarly, at this point it will be 0.
Yes, sir.
Now look at these points. There the slope is maximum.
Yes, sir.
So these will correspond to some peaks in derivative, maximum value.
Yes. Yes, sir.
right?
Yes, sir.
And what is the slope just after 0? Positive or negative?
Sir, negative.
So
Uh,
this will be negative, right? So that's why
yes,
you go downwards.
yes, sir.
And at this point you will have a maximum slope which will be also negative. So this is the maximum negative point you are getting in the derivative.
Yes, sir.
Similarly, as you are moving further right hand side, your slope decreases, modulus of the slope decreases, but it still remains negative, and at this point it becomes 0. So you get this much trace. Similarly, you follow for the right half of the part. So here your slope starts to become positive. Here it will be maximum positive slope, and there again it will decay and it will be 0. Okay.
Yes, sir.
So from this kind of plot, you will be able to draw the derivatives, right?
Yes, sir. Sir, is there any guess for the point of inflation? Uh, point of inflation?
Point of inflection you will get by looking at the curve, okay? Where you
Yes, sir.
have the maximum slope. Now let me draw another derivative. So it has nothing to do with your any formulas and all. These are just concepts. So now I want to draw this d square y over dx square. So what should I look at? This plot and take the derivative, right?
Yes, sir.
So at this point I have 0. At this point I have a maxima, local maxima, so I will have 0. At this point I have some positive slope, right?
Yes, sir.
Some positive value will be there. At this point I will again have some 0, so I will have this, and this point I will have a 0. Here I have a maximum slope, maximum slope. This maximum slope is negative. This maximum slope is somewhat positive. Okay, slope maximum will be here, but there also some positive slope will be there. Similarly, here also some positive slope will be there. Here we have already computed it is a local minima, so there will be 0. So there will be a what is the slope at this point? This will be negative slope. So some negative slope will be here. So if you join these points, you will get a plot something like this. Okay.
Yes, sir.
So now notice that if I take this point, this minima point, okay, this value. So what is the curvature at this point? Is it positive or negative? This is the curvature, right? This is slope, this is function, this is slope, this is your curvature. So at this point the value is positive, right? Above 0.
Yes, sir.
So for this case, this kind of functions or electrons, your del square E by del K square is positive. So your effective mass is positive, okay?
Yes, sir.
Similarly, if you draw for holes, now let me just reverse it and draw for holes in the red curve. So what will it look like? It will just be the opposite.
Yes, sir.
Then it will also just be the opposite. So you see the curvature for holes, it will be negative. Thus, at this point, your m star is negative because this is for holes, right? And this is for electrons. Do you get it?
Yes, sir.
So for holes, the curvature is negative.
Negative.
That's why the effective mass is negative. Now, suppose I have a higher field. So higher field in electronic sense, electronic higher field, that means generally what do we think, that whenever there is a positive charge there will be high field, right, and high energy. But in our convention, high means electronic energy is high, that means high field means higher accumulation of negative charges. So suppose I have a negative charge, okay, and a hole is sitting somewhere here which has a negative effective mass. So what kind of force will it experience? It will experience an attractive force, right? Okay, so particles with negative effective mass experiences attractive force whenever they are nearby a high electronic field. The term electronic field is very important because it is counterintuitive to our knowledge, whatever we know regarding the normally high field means we, what do we think? If it is a battery polarity, we think that the field lines are there. Here field is high, here field is low. But in our case, the convention is opposite. When you are talking about band structures, band diagrams and all. Okay. So regarding this, the effective mass being negative indicates that particle behavior is unconventional and deviates from the standard free particle model. This is not true because holes also we are considering it as a free particle. That's why the concept of effective masses of holes are there. The phenomenon of negative effective mass is still subject of ongoing research and complete implications are yet to be understood. This is also not true. We know sufficiently to deal with the solid state physics and take into consideration about this effective mass. Negative effective mass implies that the particle experiences an attractive force towards the region of higher potential, leading to a unique electronic behavior. This is true. As we have discussed, particles with negative effective mass are more stable and higher conductivity compared to particle with positive effective mass. This is not true. Conductivity has nothing to do with nothing to do with your sign of the effective mass, but it has to do with the modulus or the magnitude of the effective mass. Can you tell me how? How does conductivity depends on effective mass?
Sir, mobility
Mobility
is,
is q tau over m star,
yes, sir.
and conductivity is 1 over carrier times charge times mobility, right?
Yes, sir.
Okay, so let's move on to the next problem. So this is density of states in 3D bulk, slab and wire in 1D. So how does it behave? It behaves like this. This you can refer the lectures, okay? 3D means your crystal, the density of states, okay?
Yes, sir.
And for 2D, like nano sheet,
Graphene like
like
substance.
your graphene. And there are other also 2D materials nowadays. MOS2, graphene, and there will be your phosphorine, black and blue phosphorine. Okay, these are then your ZRS3, many higher kind of your this. If you go into research in your 2D materials, you will find out this kind of stuffs. And 1D, what is the implication?
Quantum dot.
Quantum wire, right?
Quantum
Quantum
dot wire.
wire or nanowire. For example, your carbon nanotube. And what about 0D?
A quantum dot.
So any interesting news you have heard recently regarding quantum dots?
No, sir.
So this year's physics Nobel Prize has been given to the inventors of the quantum dots. Okay.
Yes.
So okay. So let us solve this question. Let's say I have a undoped intrinsic semiconductor. Now I dope. Okay. Let me highlight. Now I dope the semiconductor with group 5 impurities at this concentration. Obtain a doped semiconductor such that the conduction completely dominated by electrons. If I cut a sample of the cubic shape, tell you the resistance is 1 milliohm. The mobility of the electron is to be found out. Okay. What do we know? R is rho L by A. Rho is 1 over sigma L by A. What is sigma? L over Q N mu N plus Q P mu P
Okay.
times A. Now it is mentioned that ND is your 10 raised to 20 centimeter cube. So you can assume that your N is also equal to ND plus 100% ionization is equal to 10 raised to 20 centimeter cube. So your P is almost equal to like one particle, right?
Yes, sir.
Why? Because Ni square by P, law of mass action. So you can almost ignore this quantity. So you will have your L over Qn mu n times A. L, your R is given as 1 milliohm. L is given as 1 centimeter, right? N you know 10 to the power 20 centimeter cube. This is your 1.6 times 10 raised to minus 19 coulomb. Mu n you need to find out. A you need to know 1 centimeter square. How do you know that? Because you have asked to find out the mobility for the your resistance is given for a unit cube. So your area is 1 centimeter square and your length is also 1 centimeter square or 1 centimeter. Okay. So from this you will be able to find out your mu n, right? So if you plug in all the values, you will find out your mu n to be around 625 centimeter square per volt second. Okay. I know that I believe that you can do the calculations. Okay. From this to this, all things are known. Only you need to find out mu n. Okay. So another problem, let's tackle that. An n-doped semiconductor having a doping concentration like this is used for a metal semiconductor Schottky contact. The junction of the metal semiconductor is this and the region extend upon this. The semiconductor permittivity is this. So built-in voltage is given. We need to find out the value of A. So what is the first step? What is the first step? How do we solve metal semiconductor Schottky contacts? Band diagram, right? First step is to draw the band diagram. So you will have band diagram something like this. This will be your contact. This is your E0, EC, EF, EV. E0, EF. Yeah, metal semiconductor work function. Metal semiconductor work function to calculate built-in potential, I do not think that it will be required. let us see how to solve this problem. Okay, and also in one lecture I mentioned that if this is the case, how will the profile field potential profile look like? Do you want to comment? Potential profile is just the opposite, right?
Yes, sir.
If
Minus sign is there.
minus sign is there, right?
Yes,
So
sir.
this will be your phi profile. And what will be your electric field profile?
Differentiation of this.
Differentiation of this and with a negative sign, right?
Yes, sir.
So this is your, let's say, x equal to 0, and let's say somewhere here is your depletion, x equal to x depletion is equal to 2 over a, right? So your electric field will be, it is maximum, it is maximum at the junction and 0 at this place. So this is positive slope, so I will go negative because electric field is minus d phi over dx. So electric field will be something like this. Okay,
Yes, sir.
so at this point electric field becomes 0. So now how to solve this problem? If such kind of doping profile is given, we know our Poisson equation. Start with Poisson equation, that is your del square phi over del x square equals to minus rho of x over epsilon s. So del square phi over del x square is equal to minus q times n of x over epsilon s. So if you integrate it once, you will have d phi over dx is equal to, you have here what, q times n0 e to the power minus ax over epsilon s, right? So if you integrate it once, you will have q n0 e raised to minus ax over epsilon s times minus a plus some constant. Let's say, how to find that constant? We need some boundary condition. And what is that boundary condition? First, let us write this in this form, electric field form. So this will be minus q n0 e raised to minus ax over a times es plus some c. Let's say we call it minus c, so plus some c. So this is your electric field E of x. We know that E of 2 over a is equal to 0. That will give me c equal to q n0 e raised to minus 2 over a times epsilon s. If I put this in this equation, right? Now let us put this back to this equation, the primary equation. So I will have d phi dx is equal to q n0 e raised to minus ax over a times epsilon s minus q n0 e raised to minus 2 over a epsilon s. So now I need to integrate it once more. So phi of x would be q n0 e raised to minus ax over minus a square times epsilon s. Here q n0 e raised to minus 2 a epsilon s. This is a constant, so only x will be there, and some other constant, let's say c1. Okay. What is my built-in potential? Built-in potential is this phi bi. That is nothing but phi of 2 over a minus phi of 0. Okay. So if you take phi of 2 over a minus phi of 0, what will you have? in this case you will have Qn0 a square epsilon s e raised to -2 and -0 will give you Qn0 over this square times epsilon s, and from the second term you will have your Qn0 this square over a epsilon s times 2 over a, right? So if you see, it will be Qn0 over a square epsilon s this term minus, there is a minus 2 and there will also be this minus, right? So you will find out that it will be -2. So this quantity is nothing but your a, because this is given as a Qn0 over a square epsilon s. Okay, so by equating you can compute that this will be something like this. So the main crux of the problem is that whenever such kind of question is given with your metal semiconductor Schottky contact, you first start with energy band diagram. First start with your energy band diagram. Energy band diagram is step 1. Once you know the energy band diagram, remaining everything is known to you, and you just need to know the Poisson equation and this boundary condition. Okay, so these are the trivial stuffs which you need to remember in the exam. Okay, the process, how to go if something is given, how to compute the other things. In my earlier sessions I have discussed in detail and also given you the algorithm how to solve this kind of questions. If rho is given, then what should you do? If energy band diagram is given, what should you do? If suppose electric field is given, then how to approach in both sides. Okay,
Sir,
so let's, yeah,
sir, this type of question where we get for practice,
this, okay, for practice,
which is
uh,
relevant for gate only.
okay, which is relevant for gate only. So I have told you earlier also that for gate, what you do, there is a book of some, I'm not, Palnitkar or Kanetkar, I'm not sure. There is a bank kind of book. Okay, one thing you can do, you can send me an email. I think I had that for my students. Okay, just send me an email, I'll share you the PDF. Okay,
Yes, sir.
that book is there, and previous year questions mainly, previous years 25 years questions. Okay, and your this kind of questions you will find in your Banerjee's treatment book also. Banerjee's treatment exercise and SMG exercise. Okay, and that book is a like a question bank for gate. You know, it has 5 volumes, so that has so many different types of questions. So there, from there you can practice it. Okay,
Yes.
so let's see how much we can do. So this threshold voltage, I think you can find out easily. So it will be what, your VFB plus 2 phi f plus gamma root over 2 phi f, right? What is this? Drop across, this is drop across silicon, this is drop across oxide, right? We know, right? Vg equals to VAB plus psi s plus gamma root over psi s. That is nothing but psi ox. Okay, and at threshold voltage at Vg equals to Vt, psi s is your 2 phi f, and your gamma is nothing but 2q epsilon s Na over C ox, and your C ox is nothing but epsilon ox over T ox. Okay, you plug in this formula and you will get this. So yeah, what I wanted to discuss is this problem. Can you tell me that what is the answer? What would be the answer, or what do you mean by Debel actually? If you have any idea. I discussed very briefly in one lecture. What is Debel? Drain induced barrier lowering. Okay, it is a short channel effect. So what is the purpose of a transistor? The purpose of it, if you see the your IDVD curve, right? Let's say this is your ID, this is your VD, this is VG1, VG2, VG3, VG4. So generally, most of the time, you will be operating in this region, right?
Yes, sir.
So what is your GDS at this location ideally?
GDS should be 0.
GDS
Resistance
is
should be
0,
infinite.
and what should be GM? We want it high, right?
Yes, sir.
Why do you want it high?
Uh, when we
Be-
make amplifier, it will be parallel with load. So we
no, no, not like that. You can think it in this way. Okay, this is a better approach to think. Suppose you are at, let us say you are at one VG, particular VG. Okay, so if you take this VG and you are walking on this curve towards this, do you want to see any slope?
no,
You do not want to see any slope. That means you want no change in current, in your drain current, when you change drain voltage, right?
yes, sir.
Now tell me that what do you want in from gate side? A small change in gate voltage, a small change in gate voltage
Large change.
should give me, because we prefer that, right?
Yes, sir.
Should give us large change in current. That is your GM, right?
Yes,
And this is your GDS. So suppose how you, from this plot, what do you want to see? How can you see if you have a fixed VD? So you draw a perpendicular line, right? Vertical line. That means you are fixing at one VD. Let's say VD1, and then you are moving, and then you are moving from this location to this location. Means you are changing your VG. So you want to see your current level to change, right?
yes,
So this is actually what is the transistor action we want. Okay, transfer resistance. Remember I taught that in BJT. Why
yes,
it
sir.
is called transfer resistance or transfer resistor? From that that name transistor came. So this is basically the crux of the transistors. Now it is fine in the long channel case. What happens is that let's say this is your MOSFET, okay? This is your MOSFET, N plus, and this is the oxide, and this is your gate terminal, right? Gate terminal, this is source, gate terminal, this is source terminal. So what do you want? What is the same statements I am going to tell you in the physics point of view, from the device point of view. So whenever you are changing your gate voltage, so you want your, first there will be depletion layer, and there will be inversion layer, right? So with a change of gate voltage, your inversion charge Qi changes. Okay. So that leads to change in current. Do you agree with that?
Yes, sir.
But if suppose I am in strong inversion, and that means my channel is present, but I am increasing Vd. So I am increasing Vd. So should it have any change in Qi? Because I want my ID to be constant, right? Do you
Yes,
see?
sir. Yes, sir.
That means I do not want any change in Qi
Yes, sir.
with Vd.
Yes, sir.
Is that clear?
Yes, sir.
So with Vg I want all the change. All of the change in this world I want from Vg, not from Vd. Okay. So that is what is desired. Now, what happens in case of short channel devices? So suppose here you have your short channel this short channel stuff, okay? So then also you will have some depletion layer around it. Can you see that your drain and source depletion layer have started to interfere with each other? Earlier, what was the case? If a long channel I would take, if suppose gate voltage is at flat band, okay? So there should not be any kind of charge. So these stuffs will be far away from each other. So there will be nothing will be there. So no conduction, okay? Now, these two boundaries, this boundary and this boundary, in case of short channel, start to come closer and start to interact, okay? So due to this, what happens is that now same thing I am going to tell you in a okay, let me finish this part. So whatever is happening in this place, who was controlling that earlier?
Gate.
So in this case, whatever is happening in this place, who will control that? You can get a decent amount of control with drain, right?
Yes, sir.
But you do not want that. Okay? We do not want that. We
Sir,
want,
how
yeah,
sir, how drain control this? This is, sir, depletion charge. Which charge is this?
any charge. For the time being, I am telling you, let us think about the depletion charge.
Yes, sir.
Inversion charge we can go later, okay?
Yes,
Because
sir.
what is your threshold voltage? Threshold voltage, actually, what is your threshold voltage? If you can dig deep down, you will see that your inversion charge and depletion charge are same. Okay?
Okay.
So now what happens? Actually, initially that substrate will deplete, then only inversion charge will appear.
Yes, sir.
Now in the channel, if suppose you already have depletion charges, so for a very small voltage you require to create inversion charge.
Yes, sir.
So this kind of phenomenon, this is the effect of Debashish subthreshold. Okay.
Okay.
So now understand it in this way that gate controls this area, right? The channel area
Yes.
for
Yes, sir.
long channel, but for short channel, drain also start to control that. That is not desired. Okay. The same
Yes.
thing we can explain with energy band diagram. Suppose I have a long channel. This is short, this is long. So now let me just draw this thing. This is n plus, this is n plus, this is p. So if I take a line across this and draw the energy band diagram, how will it look like? If I draw the energy band diagram in this cut section, let us say first we take equilibrium. So it is n plus. So here will be EC, here
Yes,
will
sir.
be EB, this will be n plus, and this is P between. So here will be EC, here will be EB, okay.
Yes, sir.
So this band diagram will look like something like this tub like nature, okay. This is the different band diagram from the MOS, okay. MOS, in which direction we draw the band diagram? This direction, right?
Yes, sir.
This is your oxide and this is your metal layer, let's say. So we draw the vertical band diagram for in case of MOS, the thing you see, right? This is your oxide, you see like this. This is one kind of band diagram in that direction, and this band diagram is in the horizontal direction. If I take from, if I just go beneath the interface and draw from drain, from source channel to drain, okay.
Yes, sir.
So now what happens when you apply gate voltage? Let's say positive gate voltage you are applying. So this will feel some positive voltage. How will the band move if you apply a positive voltage? How does the energy bands move if you apply a positive voltage? It moves up or it moves down? Remember, these are electronic energy, right? So
Yes.
positive voltage means it will move down.
Yes, sir.
Okay. If it is moving down, that means what? The electron sitting in this source area can now start to move and go to drain side. So what is effectively happening is that this barrier, what it was seeing earlier, to cross from source to drain side, because what is happening? Ultimately electrons are moving in the channel, right? From source to drain, and current is flowing in the opposite direction, right?
Yes, sir.
So as you apply the gate voltage, your this barrier reduces,
Yes,
so
sir.
more and more electrons can flow. Now how can you catch the electrons? You need to apply positive voltage at the drain side. So how will that look like? If you apply positive voltage, everything will move down, right?
Yes, sir.
So this is when Vd is greater than 0. Okay. Now let me discuss about the short channel very briefly. For short channel, what happens is that this thing is very narrow. Okay, this is your EC, this is your EV cell. So this distance will be very small. Now suppose your gate is on or your barrier is somewhat lowered, but it has still not crossed your threshold voltage. Okay, so that means there is still some barrier is there. Now you suppose you are applying some VD greater than 0. So what will happen? This will come down, drain side energy bands. So this will start to come down like this. You see what is the effect it is giving? Due to VD, change in VD, your source side barrier is reducing. Okay, suppose this is a long channel. If you are pulling this part down, drain part down, this part remain intact. Okay, now suppose this is a short channel. So whenever you are pulling it down, this part is also started to come down. Look at this place. This barrier, whatever was there, this starts to reduce. Now the barrier has become this. So what happens that more electrons can flow now over the barrier. So
Yes, sir.
that means there is an increase in current. Okay, increase in current due to Debel, and this due to the effect of drain voltage, due to the presence of drain voltage, the barrier at the source side is lowered. That is why it is called drain induced barrier lowering. Okay, this is a short channel effect. Whenever your drain and source are very close, if your drain barriers are pulling down, then your source side barrier is also started to come down, which will not be the case if it is a long channel MOSFET. Okay, so this is a Debel. These are the same things. Okay, this thing, whatever I have told here, this is by the way called charge sharing concept. Whatever I have discussed here, these are all the same things. So what will be the trace of Debel in this? There will be some increment of current, like CLM only, right?
Yes.
In channel length modulation, you will also have some increment in current, right?
Yes, sir.
Similarly, in case of Debel also, you will have certain increase in IDVD. The GDS will not be ideally 0. So whenever you see a IDVD and there is this kind of slope is there, for a short channel device it is very hard to tell for us device engineers that whether it is due to Debel or it is due to channel length modulation. And there are also other effects like substrate current induced body effect. Those are higher order stuffs. Okay, so
Yes.
remember that in short channel devices this GDS will not be 0. It will have some slope. So that is the signature in the Debel. So we do not want drain influence in the channel region. What is the other way? Suppose you are in a wrestling match. Your opponent is becoming stronger. So he started to overpowering you. So what is the method you can win? You cannot
Yeah.
do anything about your opponent's power, but you need to
Increase
defeat
our
him.
power.
Increase your power, right?
Yes.
Similarly, what power we need to increase? We need to increase the power of the gate, right?
Yes, sir.
So how do you increase the power of the gate? There,
Applying high voltage.
no. Applying high voltage is not an option. That is a different case. So you see, you tried earlier. Where was the gate? Gate was only at the top.
Yes, sir.
Now you do wrapping around of the gate like 3D structure. Okay. Earlier you were taking advantage only from the top, only from the surface.
Yes,
Now
sir.
you are taking advantage of the two sides also. You raise the gate. What was our gate? Earlier we had this kind of structure, right? These were the gate, and beneath that there were this kind of stuff, and here would be my your source diffusion region. So earlier, what was my gate? Gate was this much only, right? Only from the top. Okay.
Yes, sir.
So only one dimension you are taking care of. Now what you do? You raise the channel itself. You raise this region itself. So you have oxide here, and you wrap around the gate. That means you wrap around the gate. This will be your gate. And you put your source contact somewhere here and your drain contact somewhere here. So these kind of structure are known as FinFETs or 3D FETs. So you see, these are the planar structures, right? Here was your this N plus regions, right? And these are your gate. This is what we have discussed, right?
Yes.
So now what is there? This is a double gate structure. You do what? You do what? You use two gates. In the beneath the body also you can use another gate, so that your entire gate control increases. So this is your double gate structure. In this case, what they have done? This is the gate notation. Okay, the orange one. So this is so. Now here will be your, somewhere here is your source, somewhere here is your drain, and the transport is going in this direction. But you see that around your channel you have the gate wrapped around, right? So this is called your FinFET, and these are like a fingernail, right? Human finger. So this is why these are called your FinFETs. And another thing, this is another topology is there. Omega gate is also there. This is GAA. This will be all nano air, right? Where your 1D Poisson equations come into handy, or your 1D density of states. This kind of structures, right? Where your channel is wrapped around entire side, there will be gate. After oxide, there will be entire side, there will be gate. So why would be your source and drain contacts? Somewhere here will be sitting your source and drain contact, and transport will be happening in this direction. Similarly, this is what they are using in your current Apple iPhone 15. Okay, the transistor in Apple iPhone 15 are of 3 nanometer technology from TSMC, Samsung and all. They are using this kind of GAA nanosheet. Nanosheet means there is this same thing, same concept, they are using multiple times. This is someone, this is another one, this is another one. So gate control they are increasing. So by increasing gate control, what are you achieving? You can reduce your channel length, right?
Yes, sir.
Why? Because as you reduce your channel length, your drain starts to overpower the gate, but you are increasing your power of the gate further. Okay, so these are the new kind of structures which you will study when you go to your higher studies. But just to show that Debel is only one short channel effect which you can which you can overcome using this kind of things. Still there will be signature of Debel, CLM and other stuffs, but that is how life is. Okay, so on this note I would like to complete the session. So this is just to show you a flavor of what you are going to see in future. Okay, how the MOSFET has evolved. In this course we have only discussed this. As you move along, you will start to encounter this kind of stuffs, and this is state of the art, means what is happening right now in the industry. Okay, this is also important for some radio frequency applications, some SY kind of stuffs. So all this you will find your when you open your iPhone 15 or your any Samsung phones or any smartphone, you will see everything in between. Okay. Okay. So can we end the session today?
Sir,
Yeah.
sir, will you draw the uh, uh, MOSFET diagram and show the potential at sir? Yesterday you have drawn VG and V channel and V drain,
Okay.
sir.
That part.
Yes, sir.
Okay. Just let me see if I have that handy. This part. Okay. Let's do one thing. Do you be online? I will just end the recording. Okay.
Yes, sir.
Okay. So let's end here today.